Europa's ocean has more water than every ocean on Earth combined. It sits beneath kilometers of ice in total darkness, warmed by the gravitational pull of the largest planet in the solar system. Scientists believe it may harbor the conditions for life, and we will never colonize it. Not in your lifetime, not in your children's lifetime, possibly not ever. That statement isn't pessimism, it isn't a failure of imagination, it is the cold output of physics, biology, and engineering reality, three disciplines that don't care about our dreams. Europa is one of Jupiter's 95 known moons. It's roughly the size of Earth's moon, but the comparison ends there. Where our moon is a dead, dry rock, Europa is an ice-covered world with a liquid saltwater ocean estimated to be between 60 and 150 kilometers deep. That ocean is kept liquid not by proximity to the sun. Europa gets about 25 times less solar energy than Earth, but by tidal flexing. Jupiter's immense gravity continuously squeezes and stretches Europa's interior, generating enough heat to keep water liquid beneath a frozen crust that may be anywhere from 10 to 30 kilometers thick. By almost every metric scientists use to evaluate habitability, Europa checks more boxes than anywhere else in the solar system outside of Earth. That's why it captivates us. That's why it haunts us. And for years, the dream has been building. NASA's Europa Clipper mission launched in 2024 to study the moon in detail. Scientists, engineers, and science fiction writers have speculated about what a crewed mission might look like. There's a version of the future where humanity reaches Europa, drills through the ice, and drops a submarine into an alien ocean, where we make first contact not with something from another star system, but something from our own backyard. That vision is intoxicating. The idea that life, actual biological life, might be swimming in the dark beneath Europa's surface is arguably the most profound possibility in all of modern science. If we found it, everything changes. Our understanding of biology, of Earth's uniqueness, of the universe itself, rewritten in an instant. But getting there requires surviving a journey that begins with a number most people can't process emotionally. Europa orbits Jupiter at an average distance of approximately 628 million kilometers from Earth, depending on where both planets are in their orbits. To give that some texture, the distance from Earth to the Moon is roughly 384,000 kilometers. The distance from Earth to Mars at its closest is about 54 million kilometers. Europa, at its nearest, is more than 11 times farther than Mars. The Galileo spacecraft, launched in 1989, took 6 years to reach Jupiter using a series of gravitational slingshots around Venus and Earth. A direct trajectory with current propulsion technology would take between 3 and 6 years one way, depending on launch window and mission architecture. 3 to 6 years in deep space, in a vehicle, with no resupply, no rescue, no return window waiting for you on the other side. The fastest spacecraft humanity has ever built, the Parker Solar Probe, reached speeds of around 690,000 kilometers per hour by using the sun's gravity to accelerate, but that approach only works near massive gravitational sources. In deep space, heading outward toward Jupiter, you don't get that advantage. You burn your fuel, coast, and wait. The New Horizons probe, which flew past Pluto, traveled at roughly 58,000 kilometers per hour. At that speed, reaching Europa from Earth would still take over a year under ideal conditions, and you wouldn't be arriving refreshed. You would arrive biologically compromised in ways we will get to shortly. But before the journey even becomes the problem, there is a barrier around Europa that functions less like an obstacle and more like a death sentence. Jupiter is the most powerful magnetic field generator in the solar system outside of the Sun itself. Its magnetosphere is enormous, so large it would appear larger than the full moon in Earth's sky if we could see it. And trapped within that magnetosphere is a radiation environment of extraordinary violence. The region around Europa specifically sits inside Jupiter's most intense radiation belts. The surface of Europa receives approximately 5,400 millisieverts of radiation per day. To put that in context, the annual radiation limit for professional nuclear workers is 50 millisieverts per year. A lethal dose for a human being is considered to be around 4,000 millisieverts received over a short period. Europa's surface delivers that lethal dose in under 24 hours. There is no spacesuit currently in existence or in any serious stage of development that can shield a human being from that level of radiation. The shielding required would be so heavy it would be nearly impossible to move in. The electronics of any spacecraft approaching Europa require special radiation hardening just to survive. The kind of shielding that adds mass, complexity, and cost to every system. For humans whose biology evolved inside Earth's protective magnetosphere and atmosphere, Jupiter's radiation belts are not a challenge to be engineered around. They are, with current and foreseeable technology, a hard biological ceiling. Assume for a moment that somehow the radiation problem was solved. Assume a spacecraft with sufficient shielding delivered a crew to Europa's surface. What they would find is a frozen wasteland scoured by radiation, sitting at a surface temperature of around -160 degrees Celsius. Beneath their feet would be the ice shell, that 10 to 30 kilometer crust separating the surface from the ocean below. Drilling through it is not a trivial engineering problem. It is one of the most complex challenges in the history of exploration. Concepts like the cryobot, a heated probe that melts its way down through ice, exist on paper and have been tested in Antarctic ice sheets here on Earth. But Antarctic tests involved ice a few kilometers deep at most, in an environment where communication with the surface is instant, repairs are possible, and a rescue team is a helicopter ride away. On Europa, a drill would need to penetrate up to 30 kilometers of ice, in a radiation-saturated environment, with a communication delay of up to 52 minutes each way to Earth. If it gets stuck, it stays stuck. If it floods, it floods. There is no contingency. There is no engineer on site. And that's where the cascading nature of these problems becomes impossible to untangle, because you cannot solve them sequentially. The radiation problem and the distance problem and the drilling problem are not a list you check off one by one. They exist simultaneously. While your crew is irradiated on the surface, their bones are losing density from months of microgravity during the transit. Bone mass decreases at roughly 1 to 2% per month in microgravity. On a 6-year round trip, the skeletal degradation would be catastrophic regardless of exercise countermeasures. The heart, which is a muscle, shrinks and weakens. Fluid shifts toward the head, increasing intracranial pressure, flattening the eyeball, damaging the optic nerve. Astronauts on the International Space Station, which is less than 400 kilometers above Earth and fully resupplied every few months, experience measurable vision impairment after 6-month stays. The ISS crews return to Earth's gravity and medical care within hours of landing. A Europa crew has neither option. The immune system begins to malfunction in space. Latent viruses reactivate. Psychological deterioration from isolation, confinement, and the knowledge of absolute remoteness compounds every physical symptom. These aren't hypothetical risks drawn from science fiction. They are documented outcomes from the longest space missions ever conducted in low Earth orbit, under the best conditions humanity has ever achieved for human spaceflight. Europa is not low Earth orbit. It is not Mars. It is 600 million kilometers from the nearest hospital, the nearest replacement part, the nearest breath of unfiltered air. The conclusion writes itself in the language of physics. Europa colonization, not a brief visit, not a robotic mission, but actual human habitation, requires simultaneously solving the deep space propulsion problem, the radiation shielding problem, the long-duration biology problem, the remote drilling and underwater exploration problem, and the life support and resupply problem for a location so distant that help cannot arrive in any useful time frame. Each of those problems is, on its own, at the frontier of what humanity can currently imagine solving. Together they don't add, they multiply. And they do so against a biological clock that runs in years, not decades. This isn't opinion, it isn't defeatism, it is the honest output of the science we have. What it doesn't diminish is the scale of what we've already accomplished. We are a species that looked at a point of light in the night sky, sent a spacecraft the size of a school bus across 628 million kilometers of vacuum, threaded it through the radiation belts of the largest planet in the solar system, and detected the chemistry of an alien ocean through 4 kilometers of ice from Earth. We did that with mathematics, silicon, and stubbornness. The ocean is real, the science is real, the wonder is real. We may not be able to touch it, but we can see it, measure it, and understand what it means. In a universe that is mostly silence, that is not nothing, that might be everything.